Hi, this is Mrs. Villette, and in this video we'll go over section 5.2. We're looking at exact values of points on the unit circle, the definitions of the 6 trigonometric functions on a circle, and evaluating trig functions at unit circle angles. We'll start with the definition of the unit circle. The unit circle is just a circle of radius 1, centered at the origin of the rectangular coordinate system. So here we have a unit circle. And let's suppose we put a point on this unit circle. We'll put it over here in the second quadrant. We have these points x, y. We know that the radius is 1, so we actually know that that value is 1. And we can also construct a right triangle by dropping an altitude or a perpendicular line down to the positive x-axis. If we take a look at that triangle, that right triangle has an x as the base and a y as the height. So here is my point x, y up here and a hypotenuse of 1. So the equation of that circle is basically just the Pythagorean theorem. X squared plus y squared equals 1. Any point on the unit circle, notice I drew mine in the second quadrant, but any point on the unit circle would have the relationship that the square of the x plus the square of the y coordinates would equal 1, which is also 1 squared. Now we're going to define these 6 trigonometric functions on the unit circle. Actually, we're going to do it on a circle of radius r. So we're going to let P have coordinates x and y, and just be a point that corresponds to a standard position angle theta. So we don't have the angle theta on here, but what we remember is that our initial ray is always pointing towards the positive x-axis, and our terminal ray is actually going to be the ray that goes from the origin through that point xy, and so the angle theta is the angle that's right there. We're going to do the same thing as we did in the last circle, and we're going to drop that altitude. So now we have a triangle whose base is x and whose height is y, and whose hypotenuse is the radius of the circle, or r. Now the interesting thing about our trigonometric functions is even though it is saying that it's a function of theta, so this one is sine of theta, we don't actually plug theta into the formula that's going to appear on the right-hand side. So we've got the angle theta here, but it's actually going to depend on the x, y, and r values of the circle. Now for sine, it's only going to depend on the y and the r, but we're going to use all 3 of these values in these 6 trigonometric functions. You may remember from geometry, there is a mnemonic device, SOHCAHTOA, and that stands for sine being the opposite over the hypotenuse. So if I look at this angle theta, opposite of theta is y, and the hypotenuse is r. So the sine of theta is the y value divided by r. The cosine is the adjacent over the hypotenuse. So the adjacent would be called x, and the hypotenuse would be called r. So the cosine is the x divided by r. Tangent is opposite over adjacent, so y over x. And then the other 3 functions are simply the reciprocals. So the sine reciprocal is called the cosecant, and it is the r over the y coordinate. The cosine reciprocal is called the secant, that's the r over x. And the tangent's reciprocal is called the cotangent, that is x over y. So notice again, even though there's a theta over here on the left-hand side of the function definition, there is not a place that we plug theta in on the right-hand side. They're called trigonometric ratios because they will relate the sides of the triangle or coordinates on the circle to each other. So let's do an example where we have a point P that has an x-coordinate of 1/3, and we can see it's in the first quadrant and it's on the unit circle. We are going to find the values of the 6 trigonometric functions as functions of theta. So we actually don't have the theta drawn here. What we need to remember is that the initial ray is the positive x-axis. The terminal ray goes from the origin to the point. So here is my angle theta. If we started writing sine of theta is the y over the r, we would realize I need to know the y value. So let's back up a little bit and find that first. We know that the equation of this circle, every point on this circle, follows the relationship x squared plus y squared equals 1. That's just the Pythagorean theorem applied to points on the circle. We know the x is 1/3, but we don't know the y. So 1/3 squared plus y squared equals 1, or 1/9 plus y squared equals 1, or y squared equals 8/9. If I want to get the y by itself, I need to take the square root, but whenever I do that, I take the plus and minus square root. In this case, because of where my point is located in the first quadrant, I know that my y value is positive. Notice, if we hadn't had a picture, we would not have known if my angle was actually down here in the fourth quadrant, which would have had a negative y value. Now we simplify that to be a denominator of 3, because the square root of 9 is 3, and then 2 square root of 2, because you can take the square root of 4 from the 8, which is 2. Now we can go and we can write our 6 trigonometric ratios. So we'll start with sine of theta. The sine is the y value divided by the radius, and the y value is 2 square root of 2 over 3, and my radius is 1, so my answer is just 2 square root of 2 over 3. The cosine is the x divided by the radius. Now the x was given as 1/3. The radius is 1 because it's the unit circle, so I just get 1/3. Notice that I'm keeping all of my values exact. The tangent of theta is the y divided by the x, and the y coordinate is 2 square root of 2 over 3, and the x is 1 over 3. Notice they both have denominators of 3, so when I invert and multiply, those numbers will cancel, and I will get 2 square root of 2. Now the other functions are just the reciprocals, so it goes sine and then cosecant. So the cosecant is the reciprocal of the sine, or 3 over 2 square root of 2. We will rationalize that by multiplying by root 2 over root 2, so we're really just multiplying by a 1, and I get 3 square root of 2 over 4. Notice that the root 2 times root 2 gave you 2, 2 multiplied with 2 gives you 4. The secant of theta is the reciprocal of the cosine, and the reciprocal of 1/3 is just 3. And then the cotangent of theta is the reciprocal of the tangent, so 1 over 2 root 2. And again, we rationalize. We're just multiplying by the radical part, and I get square root of 2 over 4. At this point, I think this is the first part of the video, and you can go ahead and pause and come back to the second part of the video later when it's assigned, or if you'd like, you can go ahead and keep watching the video. Okay, at this point in the video, you should have figured out how to find all of the exact coordinate points for our unit circle angles. And those unit circle angles are things like pi over 6, pi over 4, pi over 3, pi over 2, and then reflections of those angles in all the different quadrants. In order to be successful in this class, you really do need to memorize these and be able to visualize these angles. So when I see something like sine of 2 pi over 3, the first thing I'm going to do is locate the angle 2 pi over 3. So I know that 2 pi over 3 is in the second quadrant because pi over 3 is right here at 60 degrees, so 2 pi over 3 is another 60 degrees. So 2 pi over 3 is 120 degrees. And I go ahead and I draw that embedded right triangle. And I know that on triangles like this, it's a 30, 60, 90. The shorter side is a half, but because we're in the second quadrant, the x-coordinate will be negative 1/2, and the y-coordinate will be root 3 over 2. And we're on the unit circle, so this is a radius of 1. Now we could do this on any other circle, and those side lengths would scale up appropriately. The nice thing about the trig functions is they are ratios though, so if the y value scaled up, so would the radius value, and so the sine value would stay the same. For us, our y value is root 3 over 2, and our r value is 1, so I just get positive root 3 over 2. Okay, now for pi over 6. Pi over 6 is 1/12 of the way around the circle, or 30 degrees. And again, that's that 30, 60, 90 triangle. This time the x-coordinate is root 3 over 2, and the y-coordinate is 1/2. Tangent is the y divided by the x. So 1/2 divided by root 3 over 2. They both have denominators of 2 that will cancel. So now I have 1 over square root of 3, and I rationalize that. Eventually you'll get to the point where you can see what the rationalized answer will be without doing the building of the fractions. This ends up being root 3 over 3. Okay, 11 pi over 6 is 30 degrees off of 360 in the negative direction, but as a positive angle it would actually go all the way around like that, so it would be like 330 degrees. Again, this is one of those 30, 60, 90 triangles. The x-coordinate is root 3 over 2, the y-coordinate is negative 1/2 because we're in the fourth quadrant. The y value is negative, and sine is the y over r, so negative 1/2 over 1, which we don't really need to write. Okay, cotangent of pi. Pi is 180 degrees. This ordered pair here is negative 1, 0. Now cotangent is the reciprocal of tangent, so it's the x over y. The x-coordinate is negative 1, the y-coordinate is 0. Uh-oh, we're dividing by 0. Can't do that, so we will say undefined. So the cotangent of pi is undefined. Okay, now we're on to cosine of 3 pi over 2. Again, I locate the angle first. 3 pi over 2 is corresponding to the negative y-axis as the terminal ray. And you can count around. Here's 0 pi over 2, 1 pi over 2, 2 pi over 2, 3 pi over 2. This ordered pair is 0, negative 1, and cosine is the x value divided by the radius. The x value is 0, the radius is 1, so I just get 0. Okay, we've got tangent of pi over 3. We've got a lot of these 30, 60, 90 triangles. Here is pi over 3. I draw my little right triangle, realize that the x-coordinate is the shorter one, or 1/2. The y-coordinate is root 3 over 2. Tangent is y over x. Y is root 3 over 2. The x is 1/2. The 2's cancel, leaving me just with root 3. Okay, tangent of 5 pi over 4. 1 pi over 4 is right here, or 1/8 of the way around the circle. So there's 1, 2, 3, 4, 5 pi over 4 is in the third quadrant along the line y equals x. Now the interesting thing about being along the line y equals x is we know that tangent is the y over the x. It doesn't really matter what the exact coordinates are because the y and the x are the same. So I can tell you that this is going to be 1. Now it just so happens that the x-coordinate is negative root 2 over 2 and the y-coordinate is root 2 over 2, and I can tell when I divide those, they're both negative, I'm going to get a positive 1. Okay, how about 7 pi over 6? My strategy for looking at these problems is not to just memorize where angles are, but to think of 7 pi over 6 as being really close to 6 pi over 6. In fact, it's only pi over 6 away, and 6 pi over 6 is just pi. So I know that in order to find 7 pi over 6, I'm going to go to pi, and then I'm going to go pi over 6 past that. The 6ths are always closer to the x-axis. And then the thirds, the pi over 3, 2 pi over 3, etc., those are closer to the y-axis. Again, it's that 30, 60, 90 triangle. The x-coordinate is negative root 3 over 2. The y-coordinate is negative 1/2. Secant is the reciprocal of cosine. So you could think of this as being 1 over the cosine of 7 pi over 6. Or it's the r value over the x value. We're on the unit circle, so it's 1 over negative root 3 over 2. I'm going to invert and multiply, so keep the 1, multiply by the reciprocal, and then I need to rationalize. So negative 2 root 3 over 3. I can always tell if I have a root in the denominator and I rationalize, whatever the radicand of the root was will end up being my denominator, and I'll move a root up to the numerator. Okay, so that is evaluating the trig functions at unit circle angles. Now notice I did those all in radians. I was thinking through and talking through in terms of degrees, but you really do need to get used to radians. You're probably comfortable with degrees. That's why I practice mostly with radians. Now the next problem is going to be finding these trig values for a non-unit circle angle. In fact, the angle isn't even provided. So we have a point 5, negative 2, and an angle associated with that point P. Find the exact values of the 6 trigonometric functions of theta. Well, the first thing that I realize is that this is definitely not on the unit circle because I have an x-coordinate of 5 and a y-coordinate of negative 2. Now, I don't even know what the radius of the circle is, but I'm going to put the point about right here. I just wanted the x-coordinate to be bigger than the y-coordinate. And I'm going to draw my triangle there. So, we need to figure out what circle I'm on. X squared plus y squared equals r squared. I know the x is 5, and I know the y is negative 2. So 25 plus 4, 29 is the square of the radius. That means the radius is the square root of 29. Notice we don't do a plus minus here because radius is always positive. Now we're just going through the definitions. So theta could have been this angle, the negative angle, or it could have been the associated coterminal positive angle. Doesn't really matter which one it is because the coordinates are going to be the same. The sign is the y over the r, and the y is negative 2. The r is root 29, and that rationalizes to negative 2 root 29 over 29. The cosine is the x over the r. So 5 over root 29, or 5 root 29 over 29. At this point, it gets kind of boring because it's a lot of rationalizing. So I'm going to go ahead and pause. You can go ahead and pause and finish, and then unpause and see if your answers match mine. Actually, as I was starting to write these out, I wanted to point out something. If you look at the reciprocals, for example, the cosine function's reciprocal, if you actually reciprocal before you rationalize, it will be a lot less work. Because if I reciprocal at this point, 5 root 29 over 29, I'm then going to have to re-rationalize. Versus just reciprocaling, if that's such a word, before I flip, it will be a lot faster. Same thing with the cosecant. So negative root 29 over 2. Okay, and that is the end of the video.